In this video, we'll examine a very important issue, that econometric issue that afflicts estimation, which is heteroscedasticity, which is the non-constant variance. So as an intuition, let me plot the fitted model SLR, and I'll plot the residuals with this plot command. Notice the behavior of residuals with the fitted values. Notice the variance as we go ahead with values, fitted values. Notice the variance is not constant. Sometimes it is high, sometimes it is low. And the way residuals are scattered around the fitted line, their variance seems to be not constant, which indicates that model may be afflicted by the issue of heteroscedasticity. To check it more formally, there is NCV test. If you want to know more about it, you can type NCV test and all the details will be provided to you. However, for now, for the non-constant variance, error variance, we'll simply run the command. So we'll type NCV test, and this is part of CAR package, CR package that we installed earlier. We need to supply it with the model object that we created earlier. So model, and first we'll try with the studentized, without studentized errors, and let's see. So let's see the output on the console. So I need to provide the fitted object actually. So instead of model, I need to provide the fitted object. Notice the p-value is very significant, which indicates, and this and simple NCV test fits the values along the fitted values, and it seems that when fitted along the fitted values, the error variance is not constant. It's varying very significantly, which is indicated by this very high value of chi-square and a very high significance level of p-value. So if you look at the p-value, it's quite high. We can also see if these residuals, they are varying with the nifty values. So we will specify the formula. This time around, we do not want to see with fitted values, but we want to see with nifty. By default, it runs with fitted values. This time we'll model it with the nifty, which is the nifty returns, and along nifty returns also we have a similar evidence. We can see that there is a very significant variance, residual variance, that is not constant. Another very interesting test of non-constant variance is BP test or Bruce-Pagan test. If you want to know more about this, you can simply type $BP test and all the details are there. So this BP test is a very interesting test of heteroscedasticity. It simply checks whether error variance is changing. So let us run the model BP test, and we'll supply the model object. Here we are supplying the model object, and we will decide whether we want this error terms to be studentized. So without studentized, again a very significant p-value, very similar to one we have earlier, which indicates a very high level of heteroscedasticity. If we studentize, let's see if we studentize the t values, error values, this time we are not able to reject the null of homoscedasticity. So when we are working with with studentized errors, probably it seems that the model is not afflicted that much with heteroscedasticity. However, when we are running this model, this test, BP test, Bruce-Pagan test, without studentized errors, then it gives us heteroscedasticity. So probably the issue is there. The issue of heteroscedasticity is slightly moderate in the sense that without student t values, it is not affecting our estimation. So just to summarize, we tried to visually examine the issue of heteroscedasticity. It appears to be the case that residual variance is not constant. However, when we conduct this using BP test with studentized errors, then our model seems to be not much afflicted by the issue of heteroscedasticity. So there is issue of heteroscedasticity, but it seems it's slightly moderate. In this video, we'll discuss the issue of autocorrelation. Often financial market returns are serially correlated, and that leads to issue of autocorrelation in error terms. A very simple test is Durbin-Watson test, which is, you can see the more detail about Durbin-Watson test with this DW test command, as we have been doing earlier. You can read more about it. Let's implement this DW test command, Durbin-Watson test. So while implementing DW test command, we need to supply it with the fitted object, which is SLR. Recall the object to SLR. If I run this command, notice that we get a true autocorrelation p-value as very high p-value, which means it is not significant, and DW statistic is close to 2. So we are not able to reject the null based on this p-value. That means as per this test, we have zero autocorrelation. Now please note, if DW value statistic is close to 2, then there is no correlation. If it is close to 0, then there is a positive correlation. If it is much more than 2, then there is a negative autocorrelation. Here it seems it's very close to 2, which is also indicated by p-value. That means we are not able to reject the null, that there is no autocorrelation. However, there is another very interesting test, which is Bruce-Godfrey test, for which you can see more details here with the BG test. So you can run the BG test and question mark and see all the details here. With Bruce-Godfrey test, let's see the issue of autocorrelation and how it affects our model. So we need to simply type BG test command and supply the model. By default, it will consider only one lag of error. So with one lag, notice there is no autocorrelation as per p-value. The BG test is statistic, which is essentially the LM test. And notice the p-value is not significant. That means we are not able to reject the null. However, please remember, many times the correlation is not because of the first lag, it can be also because of lags with the later periods, maybe second or third lag. To account for that, one can simply put the model with higher lag terms. For example, I can specify the order as 4 and see if the error term we have. Okay, so we are able to catch some serial correlation with 4 lags. That means there is some autocorrelation or serial correlation with higher order lag terms. To resolve this issue, one simple solution with the model is to add lags of returns in such model when there is serial correlation. In financial markets, a very simple and easily available solution is to add the lags of returns. In this case, maybe lags of market returns or lags of ABC returns, and see whether then issue of serial correlation is resolved. To summarize, in this video, we conducted Durbin-Watson test and BG test of autocorrelation. It seems with DW test and first lag Bruce-Godfrey BG test, we are not able to find any serial correlation, but when we examine the higher order lags with BG test, we find some evidence of serial autocorrelation. In practical situations, to account for such serial autocorrelation, one can add lag of returns such as ABC stock returns or maybe market nifty returns lags to see if the serial autocorrelation issue is resolved. In this video, we'll discuss the application of robust standard errors. Recall our previous discussion on heteroscedasticity and autocorrelation. These issues afflict standard errors, and standard errors go into the model t values with coefficient divided by standard errors, which result in t values under or over. So under or overvalued standard errors can affect the estimation by resulting in lower or higher t values. One solution that has been developed is to create robust standard errors that account for issues such as heteroscedasticity and autocorrelation. Now with R, there are various flavors of these robust standard errors. We'll discuss the 4 most prominent ones often employed in computation of standard error, the routines that are often employed. And please note, it will not affect the coefficient estimate, but it will provide us with the robust standard errors that will go into the computation of t values that are arguably robust against issues such as heteroscedasticity and autocorrelation. So one way to compute is to use HCCM. So we'll simply use our fitted object SLR and then we'll supply with the variance covariance matrix, which is HCCM. If you want to know what HCCM does, you can type question mark HCCM and it provides you with the heteroscedasticity corrected covariance matrices. So if you run this, you will find the coefficients. Coefficient will remain same, but the standard errors will be changed and they will correct the t values for heteroscedasticity corrected covariances. Similarly, we can also correct for heteroscedasticity and autocorrelation correction through VCOV HAC. This is for heteroscedasticity and autocorrelation. These are part of sandwich matrix. So you will generate another coefficient matrix with its t values and p values. You can also correct simply for heteroscedasticity depending upon the nature of whichever issue is affecting the model more. You can choose that. So VCOV HC. This will correct for heteroscedasticity only. And then there is new west white correction. So lastly, we have new west whites correction. We simply type new west white correction, and if you run this, you'll find the new west covariance matrix estimation. All the discussion is here, but for implementation, we'll use the same notation, only that instead of VCOV HAC, we'll supply with the new west correction, and there we can obtain the corrected standard errors and the resulting t values. So with this, in this manner, we can apply the robust standard errors. There are various flavors available. We can check more about them with this coef_test command. Coef_test. We can check more about them. Different variants, different flavors. How to apply all the flavors are available. We can read more about this. The four most prominent we have discussed: HCCM, heteroscedasticity corrected, variance heteroscedasticity and autocorrelation corrected, new west correction, and so on. So we can apply them to observe if there are significant changes in t values from our original values. It seems still applying all the robust standard errors, our coefficient is still very significant. To summarize, in this video we discussed the application of robust standard errors in correcting for issues such as heteroscedasticity and autocorrelation. We discussed four very prominent flavors of variance covariance matrices, that is HCCM, VCOV HAC, VCOV HC, and new west routines for correcting the standard errors in the model. Now that we have trained our simple linear regression algorithm and tested it for various econometric issues, we'll try to do some prediction using the test data. So we'll do some prediction using the test data. As a first step, we'll create a prediction object. Let's call it predict, PRED, and we'll assign the predicted values. We'll use our fitted object SLR, and we'll supply the new data, which is test data, and assign the values to our predict object. As a first step, let us visualize this along with the actual test data. So we'll plot along with the date, we'll plot our actual returns that are there in the test data. So this is test data, ABC returns. Will be plotting them. So on x-axis we have date, and on y-axis we'll have ABC returns. Or rather, let us call returns. We'll use central object as predicted returns versus actual returns. Now we would like to restrict our graph for y limit. We would like to visualize from minus 0.2 to plus 0.2, which is a reasonable limit to visualize daily data. You would not expect returns to vary too much from 20%, more than 20%. Then PCH20 will ensure that our objects are plotted as solid dots. We want them to plot in red colors. Also, let us specify the type as line L, type L. So there will be a solid line, in fact. Now, along with BC returns, we would also like to have our predicted object plotted along the date. So again, on the x-axis we have date, and on y-axis we would like our predict object, line width of 1. Let us specify the line width of 1 here also, although it's not necessarily needed, but just for information you can change it to 2 or any other number. if you want it more or different, the width to be higher or something. So first let us plot this. Let us plot using this command. Let's see if we are getting the object right or we are getting some error. So this object has worked. So this is the currently in red we have the actual returns in the test data. We'll add some lines. These lines, we add some lines with this command. So we'll run this lines command, and these green ones are the predicted ones. This is our predict PRED object, predict object. Now to make it more aesthetically clear, I'll also add the legend here. So legend, let's put the legend on the top right. I see a lot of empty space, so I'll put the legend on the top right. And notice, you can see that in our window, minus 0.2 to plus 0.2, sufficient amount of gap is there. So if I would have put it minus 1 to plus 1 or some higher number, it would have looked not so aesthetically good. So right now it is decent, the window is decent. In fact, I can put it as minus 0.1 also, that would be okay as well. So if I run it for minus 0.1 to 0.1, that also looks better. Now I'll add the legend on the top right part of it. So we have actual return and we have predicted return, and we like to provide the fill. So here the actual return is in red as we noted earlier, and predicted one is in green. So I'll add the green here, and then we'll run our plot. And we have the complete diagram here. Let's examine the full diagram. Notice it seems that where the green one is reasonably capturing, not in terms of amplitude but in terms of fluctuation, where the fluctuations are higher in the red ones, fluctuations are also higher in the green ones. So there is reasonable similarity in the movement. However, we need more statistical evidence to conclude that, and for that we will use our correlation command. We'll use the core command to test whether our predicted returns and actual ABC returns. So this is actual ABC return and this is our pred object. Let's examine the correlation, and the correlation is reasonably high. So this is 0.43. That's almost 43.78%. So we are able to capture the dynamics of the ABC returns to the extent of 43.78% using our regression, simple linear regression algorithm. So to summarize this video, we created a predict object. Then we plotted this predicted object along with our actual returns contained in the test data that we created. The dynamics appear to be reasonably similar. That means we are able to capture a lot of dynamics of actual return in our predicted object. We statistically examined this with our correlation measure. We checked the correlation between actual return and predicted returns. There is almost 43.8% correlation between these two entities. So it seems that our prediction algorithm has done a reasonably good job. In daily data context, this is a very high level of prediction efficiency. In this video, we'll discuss the computation and examination of out of sample fit or accuracy of our prediction algorithm. Please note that you need some kind of cost or error function to compare the model across various competing models or algorithms. Now there are various cost functions and error functions that can be employed, starting from very simple models such as MSE or RMSE errors to more complex functions. Now let us examine how to execute this in R, and for that we need library matrix, which provides us with a number of such error functions to compute. For all, let's start with this MSE. MSE computes the average square difference between two numeric vectors. So if you want to compute MSE with matrix library, you can simply type MSE test $ABC. So this is our actual return object and along with the predicted object, and you can compute the MSE measure. Now on its own, on a standalone basis, it does not have any meaning. You need some other competing model and you would like to compare this MSE, that is the average square difference between the vectors, to compare. Another variant of this error could be RMSE. RMSE computes the root mean squared error between two vectors, like we have here two returns, ABC returned and actual ABC returns in the test data and its predicted values. Also, if you want to read more or know more about these measures, you have to simply type $RMSE and you'll get most of the information here. You can check on the internet also, but most of the information relevant here can be obtained from the help window. Now, to implement that RMSE in R, you simply need to type RMSE and then test $ABC, and then you have predicted object. You can compute this measure and then you can compare this measure with other competing algorithms or models. If you may have various other competing models, maybe multiple linear regression or some other variables you want to test, and then you can put it against this value of RMSE. Then another important measure you have RAE. RAE computes the relative absolute error between two numeric vectors. So again, to compute the RAE, you have to just type RAE. And please remember, these are cost or error functions that help you understand the out of sample fit. Why we are saying out of sample? Because we are using it on test data, not on the data where we trained the algorithm. So again, we'll type test $ABC, which is our actual data along with the predicted object, and we can compute this measure of error as well. On their own standalone basis, they do not make much sense. You need to have a competing model or competing algorithm to compare with. Then you have MAE error also. MAE computes the average absolute difference between two numeric vectors. So again, the computation method is same, the implementation is same. We use test $ABC along with the predicted object, and you get the number here in the output in the console window. Similarly, you have MAPE, another very important and famous measure, MAPE of error, which is MAPE computes the average absolute percent difference between two numeric vectors. If you want to compute the MAPE, you can simply type MAPE test $ABC and you have predict object. You can compute MAPE also. Then there are a number of measures. For example, you have SMAPE. SMAPE is basically, it computes the symmetric mean absolute percentage error between two vectors. So you can compute SMAPE for test $ABC data with predict data, you get that number. In a similar manner, there are other measures, we can compute them. For example, you have MSLE. MSLE computes the average of squared log error between two numeric vectors. The computation method remains the same. Then you have RMSLE. RMSLE computes the root mean squared log error between two vectors. Similarly, you have bias measure. Bias measure computes the average amount that is actual greater than predicted. You can compute in bias in the percentage form also. You have RSE measure. RSE measure computes relative squared error between two vectors. For example, you can simply type RSE test $ABC along with predict object. Same, the syntax remains the same, and you can get the RSE object. You can also have RRSE, which is the root relative squared error between the two vectors, and so on. You can there are many measures. These were the most important ones. You can pick a number of measures and then compare this matrix along with another matrix. You can create more complex objects. For example, you can give different weights to these different errors and then create a new object as per your requirement, or some more complex expression you can create out of all these error objects and create a more complex error object to compare against competing models. So there are different flavors to it available with you. You can use them to check the out of sample accuracy of your model. To summarize this video, we discussed a number of error or cost measures to examine the out of sample forecasting or prediction accuracy of our trained algorithm. We also saw their implementation in R, and we noted that we can create more complex forms of error or cost functions by assigning weights or some complex expressions to these readily available error or cost functions. In this video, we'll start with multiple linear regression model. Most of the syntax to implement and execute the model will remain same. So let's call it MLR, multiple linear regression model. And as we did with the simple linear regression model, we'll use LM object, ABC returns, and let us add sensex returns, BSC sensex, sentiment measure. Since this is a multiple linear regression model, we'll be using a number of variables on the dependent side, Nifty, dividend announce, dividend, and we'll use our train data set to train the model. So now that we have put the expression, we have provided the expression, let us run it. Our object, MLR object, saves the entire output. So let us print the output summary object MLR. Let's call it model. Again, we are using the same naming convention. Let's see this output. Let us examine the output of this model. Notice the coefficient of Sensex and Nifty both are broad market indices, while Sensex is heavily significant at 3 star, that is significant even at 1% level. Nifty is turning out to be negative now. This is slightly surprising for us because we already saw that Nifty with simple linear regression model, that Nifty also has a positive impact. Now this, and here Nifty is not significant. This suggests that there is some possibility of issue of multicollinearity, as we'll examine in the next video. Because Sensex and Nifty both are market-wide variable, so this provides us intuition of multicollinearity issue, that because of that the coefficient and significance estimation of Nifty is getting affected. We'll examine that later. Also notice that sentiment variable is turning out to be a very significant, very significant even at 1% level. That means 99% confidence. Dividend announce is also significant. It is turning out to be at 95% confidence or 5% significance level, as we can see here, significance quotes. So dividend announced is also very significant. Notice the adjusted R-square, the power of model is very high as compared to the around 10% that we saw with the simple linear regression model. This is for the fact that there are a number of significant variables that have been added. So the overall power of model to explain the variation in returns is increased considerably to around 27.84%. However, we still need to observe the issue of multicollinearity here to resolve that. To summarize, in this video, we trained our multiple linear regression algorithm using the trained data. We summarized the output and briefly reviewed the output. In the next video, we'll jump to the resolving multicollinearity issue as we discussed in this video. We'll skip residual diagnostic, issue of heteroscedasticity, autocorrelation, and robust standard errors, because they are exactly identical to what we have already seen in the simple linear regression model. Same commands with same notations will be employed, and the examination will be done in an identical manner. So in the interest of time and brevity, we'll skip that part. We can directly apply the same codes here. Same exactly identical codes can be applied for the multiple linear regression model to obtain and examine the residual diagnostic, heteroscedasticity, autocorrelation, and robust standard errors related discussion. For more detail, we can directly look to the video topics on heteroscedasticity, autocorrelation, residual diagnostics, and robust standard errors video topics to get more information on this. In continuation with our last video, we noted that the issue of multicollinearity may afflict our estimation process, and therefore in this video, we'll examine the issue of multicollinearity in more detail. Please recall, we said that there's a possibility that some of the independent variables may be correlated, and therefore that may give rise to the issue of multicollinearity. So as a preliminary evidence or examination, we'll try and compute the correlation in the trained data set for the independent variables. Our independent variables include ABC, returns, Sensex, and we'll see which of these variables are heavily correlated. These are all independent variables that we employed in the multiple regression model. These are the main variables. We are leaving the dividend announce variable, which is a dummy variable. So chances of this variable being correlated are very low. This is dividend announce is just ones and zeros. So notice the correlation matrix that we have produced here in console, and notice the very high correlation. So between Nifty and Sensex, the correlation is almost 80%, which is a clear indication that there is a possibility of multi-collinearity because of this high correlation between Sensex and Nifty. All the other variables are though correlated, but the levels are even lower than 50%, much lower than 50%. So they may not have much multi-collinearity related effect. So let's also recall that we created our model object MLR in which we trained the algorithm. So we'll use this what is called VIF, variance inflation factor, what we call variance inflation factor, VIF, which measures the extent of multicollinearity in a model. So we'll use VIF and MLR. If this number, and it indicates variance inflation factor for different variables in the model. If the number is around 1, then multicollinearity is almost negligible. If it is higher than 2, then it is moderate. If it is higher than 5, then it is really high. Notice the multicollinearity with Sensex and Nifty variable, and both of them are heavily correlated, is 2.9, which is on the higher side, which indicates that we have to drop one variable to remove the multicollinearity issue in the model. Now that we have seen our model contains the issue of multicollinearity because of the market variables Sensex and Nifty, we would like to remove one of these variables to improve our estimation. And in the interest of that, we'll again train our model on the trained data, but this time we'll remove one of the market variables and run our regression ABC on Sensex. So we are removing the Nifty. So we are only running on Sensex, sentiment plus dividend announced, and we'll again use our trained data. Let us run this model and let's summarize this into a model object. So we'll create a model object in which we'll put our summary of the model. We'll print this model object, and again the adjusted R-square numbers are same, but notice the Sensex has much higher significance as compared to earlier. The beta, which is the coefficient of Sensex, is around 0.55. Sentiment variable is also very significant, and dividend announced is very significant. To interpret the Sensex variable, for example, 1% increase in market or Sensex leads to 0.55% increase in the ABC returns. Also, notice the dividend announced variable. Since it is a dummy variable, on average, there is a difference in return when the dividends announced. There is increase in return of about 0.0038% on that dividend announcement day, and the model is able to explain around 27.85% of the variation in the ABC returns. So we have improved our model and accounted for the issue of multicollinearity. To summarize this video, we noted that when we computed the correlation matrix, we found that the two market variables, that is Nifty and Sensex, were heavily correlated with a correlation number of almost 80%, and indicated the presence of chances of multicollinearity, which we further examined with our variance inflation factor, which is VIF. And VIF suggested that indeed Sensex and Nifty variables are afflicted by the issue of multicollinearity. So we removed the Nifty variable and then again trained our model, and the model output is reviewed in the discussion. In the next video, we'll create a predict object and we'll compare the predicted and actual test values and try to visualize them to see our out of sample forecasting efficiency. In this video, we'll create a prediction object using our test data with our trained algorithm, multiple linear regression algorithm. So we'll create a prediction object with test data. The procedure is very similar to what we did with simple linear regression model. We'll create a predict object. We'll assign the values that are predicted using MLR. This is MLR object that we have already trained object, and in the new data we will assign the test data set. So we are assigning the prediction object, creating a prediction object with the test data. Now that we have created this object, we'll try and compute the correlation between this predicted object and our actual ABC returns. So we'll use this predict object and we'll compute the correlation between predict and test, and there's a 57% correlation. Let us also try and visualize, make a comparison using visualization. So we'll first plot our actual returns. We have already seen these commands with the simple linear regression model, but still we'll run them again. So test $date, test $ABC. So with this xlab, again the same syntax, date, ylab as returns. We'll be plotting actual and predicted returns. So the central heading again here is actual versus predicted returns. Again, we would like to see the ylim here, so we would like to set the y limits from minus 20%, which is a reasonable limit, to plus 0.20. We would like to plot red color line as actual ABC returns in the test data and type as line. So this is our line type. We'll run this later with the complete thing. Next, we would like to have lines command. With the help of lines command, we'll add our predicted object. So let's call it predicted object that we have just created, and color we'll give it green. Again, the type will assign a type of line. So we are using line type. Other option is to plot in terms of points. For this kind of graph, line type is more preferable to make a better comparison. Again, we'll add legend. So like we did last time, we'll use legend on the top right side. On the top right side, we have legend, and we have actual returns first, then we have predicted return. We'll assign colors, so fill equal to, we have red as actual and green as predicted, as we have noted. So now let's do some plotting here. So I'll enlarge the plotting window for better visualization. First I'll run the main plot command. So these are my actual returns in red. Then I'll add the lines. Through lines command I'll add the predicted returns, and then I'll add the legend. Now let's zoom this graph and notice very nicely our object is capturing. As we also saw in the correlation, there was a very high correlation, and the same is reflected here. Our predicted object in green is very nicely capturing the fluctuations in red, actual returns, ABC returns. So that means our multiple linear regression algorithm has done a very nice job of predicting the returns, and that was also reflected in our very heavy correlation of 57.7% between actual and predicted returns. To summarize, in this video we created a predict object using our test data. In this predicted object, we computed the correlation with the actual test data. The correlation is 57.7%, which was very high. We also plotted and visualized the actual return and superimposed them with the predicted returns, which again confirmed that our prediction has been, the algorithm has been very efficient in predicting the objects. Now here we are not doing the out of sample forecasting errors that we did for simple linear regression model. We can go and review the video on out of sample regression forecasting video topic. In that video topic on out of sample error forecasting, we have discussed in great detail the R implementation and the interpretation of error functions. So in the interest of time and brevity, we will not repeat there. The command, execution and discussion remains identical, so we can refer to that video topic on out of sample forecasting. To summarize this lesson, we model ABC stock prices using simple regression problem with market index variable. The model is trained using training data set and various goodness of fit measures are examined. The fitted model is examined visually as well. The model is tested using test data set and various measures of out of sample fit are also examined. Next, a multiple linear regression model is trained using trained data set on multiple variables. The fitted model is visually examined and also various goodness of fit measures are examined as well. The model is evaluated on various issues related to multicollinearity, heteroscedasticity, and autocorrelation. Lastly, the model is examined on various parameters for its out-of-sample fit performance.